Okay, now you can get quiet on my account. Okay, so last time we had started talking about minimum total cost spanning trees. I want to spend a couple seconds talking about administrative stuff, and then we'll get going on our business of the day. So administratively, we now think all of your quizzes, your quiz information is in the gradebook. Yes, Wade, am I saying? No, in your SVN, sorry. Not uploaded to the gradebook yet, but all of the scores. We believe we had fixed all of our key errors with the quizzes. The exam regrades, if you have requested something or something flaky has happened to any of your exams, they are running as we speak. And the very next thing on the list of things to do is, on Wade's list of things to do, is to grade exam 7. Bye. So we think that, we believe we will have all grading information out to you easily by the time you are scheduled to take your final exam. Furthermore, one more thing, sorry I'm a little distracted here. Yes, what do we think? Okay, we'll see if that keeps going. Furthermore, quiz 11, the mysterious quiz, is going to get released to you sometime today. I think by 5 o'clock, but maybe not. It's my fault. I was supposed to finish going over the problems over the weekend, and I didn't. So, but we're working on it, and you'll have all week to do it, and it's not going to be a timed thing. Our intention is for you to be able to do this luxuriously, as many things in this class have not been. All right, so let's get back to the middle of spanning trees, in particular into the middle of Kruskal's algorithm. Last time, we sketched out an algorithm on a graph, and we kind of talked, it was sort of like talk aloud programming. This time, we're going to have 2 different levels of pseudocode, and last week in lab, I believe you actually explicitly wrote the code. So for the first couple examples that we're going to do here, we're going to go very, very quickly. What we're going to do in much more detail is the analysis portion, okay? So probably this first piece will be review. All right, so Kruskal's algorithm for finding minimum spanning trees. Oh, I did have one question. Yeah, there's a constraint on input to any minimum spanning tree algorithm that says that the input graph must be a connected graph. And my question for you is, why is that true? Why does the input graph to these algorithms have to be a connected graph? Yeah?
If it's not, then you couldn't get a single tree that contains all the nodes.
Very good. So if the input graph were not connected, then no subgraph could be connected, and the tree that we're finding is just a subgraph of the original graph. Couldn't be a tree because all trees are connected acyclic. So the input graph has to be connected in order for the algorithm itself to even make any sense. Okay? All right, so let's get back to Kruskal. Sorry about that. So the first thing we do is initialize some structures. We initialize a graph T that's intended to be our output. We initialize a disjoint set structure. For this example, I've just drawn them. And we initialize a priority queue. I intend no particular implementation of that priority queue. I just put it here as a sorted list so that I can use it easily in the example. we're going to spend a fair amount of time talking about the particular implementation of the priority queue later on. Okay, so how does the algorithm go? Remove min from the priority queue. Oh, look, there it is, AD. If A and D are in separate sets, now think about what that means. That means the find of U is not equal to the find of V. Then do the following. Add the edge to T and take the union of the two sets, indicating that now we've got sort of a sub-solution to the problem, that among each of those sets there, we have the minimum spanning tree containing their vertices, okay? And we keep going. EH, you do a find on E, a find on H. They're not in the same set, so we add EH to the graph and take the union of their two sets. Remove min, FG. F and G are in separate sets, and so we add the edge to the solution and take the union of the two sets. AB. A is in D's set. The representative of A is D. B is in its own set, so they're not in the same set. So AB is added to the structure and the union is taken. Now, here's the point at which it's possible that my sketching deviates from the actual execution of the find union, or union find structure, the disjoint set structure. I'm only sketching it here. I'm not going to try to unravel path compression in this context, okay? So this will not be an illustration of path compression, but rather just of simple unions. All right, then we take BD. We remove min from the priority queue, we get BD. We do a search on B and a search on D, or find on B and a find on D, and lo and behold, they're in the same set already. So we ignore that one. We take GE. These two are the same, so it can't possibly matter. GE is accepted. And now E, F, G, and H are all in the same ones. All right, I'm not going to keep doing this because I see some eyelids kind of drooping here. I am going to let you ask me questions if you want to. Are you good with this? I believe programmatically you've seen this kind of structure in two different contexts now, both in MP7 and in the lab last week. Officially, though, we would stop when we saw n-1 edges added to the structure. In this case, of course, 7 edges added to the structure. Okay, so let's get a little bit more serious about this. Let's look at some pseudocode. In particular, let's look at some pseudocode. Ultimately, we are going to be interested in analyzing two different pieces of this. We're going to be interested in analyzing the setup and the iteration. So this is the initialization portion of the algorithm, and this is the iterative portion of the algorithm. And those are going to come in two separate chunks, and they're going to constitute the basis for our analysis, which happens on the next page. What I want to bring to your attention here is the set of commands related to the priority queue in particular. Okay, so how does this go? Well, it looks to me like this piece is the build the priority queue piece, and this one is the only priority queue operation in the algorithm. Okay, so all of the work related to the priority queue is, number one, to build it, number two, to remove something from it. Now, we've already seen that we have two alternatives. We have two alternatives for priority queues, heaps or sorted arrays. What I want to know from you is the time to build and the time to do a remove min for each one of these cases. How many things are we going to put in the priority queue? Oh, I'll give you this too. I'll give you this notation. The size of the vertex set is n, and the size of the edge set is m. How many things are we going to put into the priority queue? M. So what's the running time of build heap? O of m. That's right. That's a key thing to remember. Okay, so you can build a heap of m items in linear time. It's one of the big asterisk facts from this class. Okay. And how much does a remove min from a heap cost you? What is it? Log of, okay, good, very good. All right, so now let's have the same discussion about the sorted array. How long does it take to sort the array? Big O of, what is it? In general, we'll use merge sort. Okay, and how about remove min? How about remove min from a sorted array? Yeah, very good. Constant time. All right, any questions? Yeah? What? Log n? Oh, shoot. Should it? Because there are m items there, right? Well, let's do a little detective work here first before I have a hard time thinking in this front 10 feet of the room. So let's do a little detective work, okay? For simple graphs, it is true that m is big O of what? N squared is a nice little term for us, yeah? And that means that it's less than or equal to some constant times n squared for many of the n's, for n above some threshold. That's the definition of big O. Now, because log is an increasing function, we can take the log of both sides and the inequality will still hold. So we're going to take the log of both sides here. So log m is less than or equal to log of cn squared, but your math teacher would snarl at you if you wrote it this way. Instead, you should write it as log c plus 2 log n, yeah? Which, I don't want to look at that. I want to blur my eyes and get rid of this constant term and that coefficient by writing big O of log n here. Okay? So you're right. In the context of the algorithm, we should have been expressing this as log m. But because m is kind of fuzzy, and because log m and log n are really the same thing, we are going to use log n in these expressions, okay? So any question about that at all? So you were right, but I was right, okay? Yeah? The product of the big O expressions. Oh, like here? Oh, that's my punchline on the next slide. So I'm not going to answer that yet, okay? All right. Any other question about this? It's a little different than you're imagining, though, Jeremy. It's not quite, I don't think it's quite the model you have in your brain, but it's close. Okay, yeah, Mark? Really excellent question. So the question is, why don't we just put an n squared here then? And you could. That would be true, right? But it's not the best we can say. Using m there means we have a way of plugging in more details about the algorithm if we know something more about our graph. So we're going to use m whenever we can if it doesn't make any difference, or if it matters. But here it doesn't matter. Here, log m is big O of log n. They're the same, whereas linearly, they are not. Okay, who asked me that question? Oh, Mark. Does that make sense? So the example is, what if I tell you that your graph has big O of n edges? Then the running time of this is n log n, right? You can say something better about it if you allow yourself the flexibility of m here. Whereas that flexibility here doesn't gain you anything, because in either case, they're both log n. Okay? Is that enough? Okay. All right, any other questions about this? Okay, so these are the salient points from this, this kind of pre-analysis. Now we're going to go and we're going to look at the analysis as a whole. As I said before, we've got the initialization plus the iterative portion, okay? And that's what we're going to do here. Let's first look at the initialization. How long do you think it takes to set up n disjoint sets? Every vertex in its own set? Certainly no worse than big O of n, right? And that's if you're counting carefully. That's if you're assuming it takes you that, you have to build it one by one rather than, yo, give me an array of size n on the heap, okay? So no worse than big O of n. It's going to get dominated away anyway. Priority queue, this is going to be either big O of m or big O of m log n. Okay? Depending on which one we choose. And then setting up the graph this way is going to be big O of n to set up the vertices. So in each case, the initialization is dominated by the priority queue operation. In the context of the heap, the initialization is big O of, oh, I guess that's not exactly true, depends. Okay, bounded below by n. And for the sorted array, it's m log n. I'll just write that term, shoot, doesn't hurt. Okay, and now we have the iterative step. I'm going to cut you some slack here. We are going to assume that all of the union find operations are constant time. We know that they aren't quite, but they're agonizingly close to constant time. And so for the purposes of this analysis, and because we're considering that these graphs aren't going to be particularly huge, relative to the number of atoms in the universe, we're going to go ahead and let all of the disjoint set operations be constant time. So that means these are constant, this is constant. How long does it take to add an edge? Assuming an adjacency list implementation, because there's no reason not to here. How long do you think it takes to add an edge to a structure? It has to be constant time, that's right. Okay, so everything here is constant time. How many iterations are there of this while loop in the worst case? Do you remember? you might have to look at all the edges. You might have to look at all the edges. So you have m iterations in the worst case. So what we end up with in the heap is m iterations at log n each. And in the sorted array, we have m iterations of constant each. Okay, everybody pick their favorite. Pick your favorite priority queue implementation. You got it? Some of you pick this, some of you pick this. Are you ready? Raise your hand if you choose heap. Raise your hand if you choose heap. Okay, raise your hand if you choose sorted array. Okay, everybody wins, right? It's a tie, obviously, though you would have to come down and make a decision. I don't know. If you set these up and you had a race, if you had a benchmarking race, I suspect this one would win just because algorithms for sorting are so good in the standard library, okay? So I think this one would probably win. But there's actually a case where this one is a good option. Somebody who chose this heap, explain to me why they did so. Somebody who chose the heap. I saw some hands. Who chose the heap? Yeah, why? It's a nice implementation. Okay, I'll buy it. I think so too. And it actually has a benefit that for dynamic graphs, that is, for graphs whose edge weights can change, it's really the only option. Or for graphs that are growing, like if new edges are coming into the graph. So the heap is really your only efficient option if your graph is dynamic. Yeah, go heap. That's right. Go heap. Best for dynamic graphs. Okay? You know, though, a sorted array isn't so bad either, because it may be the case that, number one, something else happened to sort your edges ahead of time anyway, so you might essentially get this for free. Or, number two, you've sorted them. There's no reason to ever unsort them, right? You can use them, perhaps, for other things, like perhaps other algorithms. Effectively, if you sort these edges, you're creating for yourself a sort of histogram over edge weights or a probability distribution over edge weights. And so we have reason to believe that that structure would be useful in other contexts as well, because sorting overall adds to our sort of organization of our data. All right, so this one may be good for future computation. Okay? So you can decide. And I think it's probably faster anyway. Somebody last hour pointed out that that actually you may not have to go through all m of these here. And so you may not have to go through the whole structure. So having them just sorted cuts part of this off as well. I guess that kind of argues for this one. I don't know. Doesn't matter. Uh-huh. Yeah, that's true. Yep, that's true. Okay, then all the m's are n's, though, then in that case. All right, any other question about this? So I think you know everything you need to know about Kruskal's algorithm. You've implemented it a gazillion times. You've thought a little bit abstractly about it, and we've analyzed it probably as carefully as we're ever going to analyze anything, making the implementation decisions as we go, as anticlimactic as it seems. So I have a new a new minimum spanning tree algorithm for you. It is more closely related to traversal than Kruskal's algorithm is. And you'll see what I mean by that in just a second. So Prim's algorithm, developed about the same time, relies on the following observation, that if you take any graph and any partition of the vertices into two piles, okay, take any graph in the world, cut it in half, put some vertices over here, some vertices over here, then look at the edges that cross between the two sets. The minimum weight edge will be on a minimum spanning tree. Okay, so there exists a minimum spanning tree containing that minimum weight edge. So take a look at the top example. The theorem says that edge E is a part of some minimum spanning tree. The way the theorem applies when there is a tie says that there will be a minimum spanning tree containing one of the minimal values. It may not be the case that the other one is also part of some minimum spanning tree. Okay? All right, any questions about that? So if you partition the vertices, look at the crossing edges, the minimum weight one is in a minimum spanning tree. Any question about it? And you'll prove it in 374, I think. If we had, this is one of the things, Wade, that should be added to the class. Okay. Yeah. Yeah. No, we don't have time now, not to do it carefully. We have so much else to do. Okay, so I'm going to draw one line, and I want you to tell me why. Okay? I'm going to draw one line, and you're going to speculate on why. I'm suggesting an algorithm by this line. That's my line. Yeah? Yeah, let's do that. So we're going to start with this vertex, just exactly like he said. We're going to start with this vertex being one of the partition. This is the partition. Here's one of the sets. Here's the other set. What's the implication? The only thing we know now, right now. According to the theorem, if we partition it in this way, what do we know? Yes. There is a minimum spanning tree containing this edge. Can you think of a new partition I might want to do now? So this one, is that my new next good partition? Yeah? Okay, what edge? What edge now? The one labeled 3, good. And now what's my new partition? What do you think is my new partition? Include the new node. I should have labeled these nodes, huh? Be easier. Okay, fine. Oh boy. Now what? Add the one labeled 2. Good. And where's my new? Yeah, it's like this, right? Okay. Which edge? 3, good. The one of weight 3. And now we've got a little bubble in our horizon. Okay, now what? I'm going to add one of weight 2. And just to double check, the cross between them is one of weight 4, 5, 4, 3, 2, 3, 4. Oh my gosh, I hope those are in a priority queue somewhere. Okay, etc. I'm going to quit changing color because I started doing it wrong. Okay, now what? Oh my gosh. Okay, I got a couple choices for 3, right? I'm going to choose this one. So now I've got, oh wow. Like this? Yes? Is it still 3, my best one? Oh, 2, right. Okay. And now we're out to here. Now what? Choose the one labeled 3. Good. But I don't cross that other one, do I? Oh, yeah, this one. Okay, yeah, you're right. Okay. And then better choose this one. Oh, look. If I put all these together, I have a minimum spanning tree. Yay! Any question about it? All right, so this algorithm requires way more bookkeeping than we betrayed here, right? Because I don't know how to draw squiggly lines in memory. So we're going to talk more concretely about what those supporting structures are. Okay, so here's what we're going to do. We're going to initialize a bunch of structures, none of which are going to be a surprise to you. We're going to associate with every vertex a current least cost of attaching that vertex to the solution. So hold on just a sec, okay? Current least cost of attaching V to solution. And P is the way you attach it. P of V is the adjacent vertex in the solution. Yeah, did you have a question? Okay. Oh, I don't know how to do that. If I had to, so the question is a good one. It's could you choose a node that gives you the least amount of craziness? So I think so if I had a metric on craziness, right? If I had a way of describing that, then I could attach that to the weights. And then I could make my decision based on that as well. So like if there's a tie, choose the one of lowest degree or something like that. But I don't know how that plays out. And theoretically, I don't think it probably changes anything in the context of this. Because either you're changing what a weight means, or you're just breaking a tie, which I don't think that can have bad consequences. Okay? Does that answer your question? Okay. All right, so back to this. The way we're going to initialize those D's at first is to give them all very big integer weights. Okay? I'm going to call it infinity, but you're going to come up with maxint or something like that, and all of the predecessors are null. Okay, we haven't decided on any predecessor yet. We're going to initialize some start vertex to have distance 0. We're going to initialize a priority queue this time with the D sub V's. Which means there are n of them, okay? Because there is one of those measures for every vertex. And we're going to set the set of labeled vertices to the empty set. So nothing's labeled right now. All we have is a priority queue with 0 and a bunch of big numbers in it, okay? Any question about that? All right, so now we're going to iterate over the algorithm. I'm going to go ahead and write those back in real quick. The algorithm goes like this. We're going to repeat these steps n times, once for every vertex, because we're going to be adding a vertex to the labeled set every time. I promise you that that last one, the nth one, will be a fall through. There won't be any work to be done, but I still just like I like writing that n right there instead of n minus 1. All right, find and remove the minimum D unlabeled vertex. In this case, that is A. And that is a priority queue operation. So however you're thinking about your priority queue, there it happens there. Label vertex V. I guess I did so kind of by making note of it. And by labeled, for the example, I'm going to put it behind the little advancing horizon, much like we did last time to create the craziness. Now, probably labeled is simply a flag that you're going to set in your vertex structure. Just set it. It's kind of like visited, very much like visited. Okay, and then we have this thing that we call the update. That update set merely says, use that horizon to update your best known mechanisms for attaching new vertices to the solution. Okay, so we're going to look at all the unlabeled neighbors of the one that we just labeled. So here we're going to look at this edge, and this one, and we're going to compare the weight on the edge with the current best D. Is 2 better than infinity if we're talking about cost instead of, yes, cost instead of value, right? Yes, 2 is better than infinity if we're trying to minimize cost. So what we're going to do is we're going to change this value to 2 and indicate the predecessor along that edge. Similarly for 8. 8 is better than infinity, and our mechanism for achieving that 8 is here. And finally, 7 is better than infinity, and the way we get the 7 is here. Any question about that? So now I think that we have finished one step, one iteration of this process. Let's do another one. Find and remove the minimum D unlabeled vertex. Well, what do we have for our Ds? We've got 2, 8, 7, big. I'll take 2. How about you? Okay, so we remove B, which means label it, and then update along the horizon. Update B's unlabeled neighbors. 7 is better than infinity, so I change this to 7 and indicate the predecessor. Here's something new. Are you ready for this? Is 5 better than 8? Yes. So what we're going to do is change the 8 to the 5 and also update the predecessor. So C's predecessor is now B. So that's new. We never saw that in traversal. In traversal, once we set that predecessor, we were done. But here, we're trying to optimize something, so we're on the lookout for a better option, okay? All right, and then let's keep going. Remove the minimum weight. Remove D, or remove the minimum weight D. In this case, that's C. Here's the new labeled set to the left of this line. The things we need to update are 9. 9 is not better than 7, so we're going to ignore it. 8 is not better than 7, so we're going to ignore it, and we're done with that iteration. Again, we find and remove the minimum weight D. Let's take E, okay? Is that all right with you? It's a tie, we'll take E. No, I don't hate E, and I'm the boss. Okay, we took E, we labeled it. We need to update all of the unlabeled adjacent edges. 3 is better than infinity, so F becomes 3, and the predecessor goes there. We are almost done. 3 is the least D, so F comes off. We label it. Update the neighbors. This becomes 4, and the predecessor changes. And then finally, find and remove the least weight. That's D. Label it. There are no adjacent edges to update. Okay? Yeah? Yeah? Yep. Yep. So the speculation is if we had chosen this one instead of this one, then we would have had at 4 instead of 3, but we eventually would have chosen this 3. So it creates a different minimum spanning tree, but the total cost is the same, okay, because we effectively traded this 7 for that one in this instance. That won't necessarily, there are lots of different ones you can make if you have lots of different repeats, okay? All right, so, and we're done. So where is the minimum spanning tree? Well, we just color all the predecessors. I think these are them. Okay? Any question about that? So the solution here is embedded in those predecessors. You could create a structure kind of like the T that we did the previous time. That would be fine too. It's up to you. But the predecessors are part of the execution of the algorithm and you need them. So you're not going to want to just chuck them. Okay? All right. Any question about it? So you might as well take advantage of having them instantiated if you like. All right. You good? Okay, so the only thing we have to do is to analyze the running time of this algorithm. And this is a perfect place to stop. What I would appreciate from you is taking a few minutes to fill out the ISIS forms for the semester. Also, could I have a volunteer to turn them in upstairs? It's a matter of, you got it, Mark? Okay. A matter of collecting them. The envelope is over there, and you can just run them right upstairs to the ECE office, like the main office. They'll know what to do with them. Okay, see you guys Wednesday. We're going to make it. Unbelievable.